Welcome back, everybody. In this video, we'll be starting chapter 4 and section 4.1. As always, when we start a chapter, it's a good idea to look ahead and see what it is that we're getting into and then actually get into it. So chapter 4 is about a new kind of function called an exponential function and also logarithmic functions. The chapter has a total of 8 sections in it. We're going to actually only be covering the first 6 sections. So let's give a little quick overview of those. What an exponential function is basically a function where we take a constant base, like 2, for example, and raise it to a variable power. Okay, so here if we had 2 raised to the x power, we could think of f of 3. This would be 2 cubed, which would be 8. F of 5 would be 2 to the 5th power, which is 32. So we have a constant base raised to a variable power. And notice that's different from having a variable base raised to a constant power, like a power function would have, like the x squared function you're seeing at the bottom of the screen. So here when we're doing this, we're not just kind of playing around and saying, okay, well, let's see what happens if we put the x in the exponent instead of in the base. It turns out that there's a lot of good, actual, useful, and interesting applications of this kind of function called an exponential function. This first section, 4.1, we'll look at the definition for exponential functions. We'll look a little bit at what their graphs look like and a lot of applications. Section 4.2 is shorter and focuses on the graphs of the exponential functions. There's a related class of functions called the logarithmic functions that are actually the inverses of the exponential functions. We talked about inverse functions at the beginning of this course, how if you have a function f of x, you can think about a function f inverse of x that undoes the action of that f. And so we saw that a square root function with suitable limitations was the inverse of a quadratic function. And we calculated a lot of inverses at that time. It turns out that the logarithmic functions are the inverses of the exponential functions. We'll talk more about what those functions are like when we get there. But section 4.3 introduces those functions. 4.4 talks about what their graphs are like. 4.5 has to do with properties. As you know, there's a lot of different exponent rules, right? Like x squared times x to the 3rd power. When you have the same bases, as you know, you add exponents if you're multiplying. Logarithmic functions related to exponential functions. Since exponents have a lot of different rules, it makes sense that the logarithms are going to have some rules. That's what 4.5 is about. Section 4.6 is about solving exponential and logarithmic equations along with some applications. So we'll see more what that's about when we get there. But that is where we're going to go in this chapter. So we'll be starting here with section 4.1 on exponential functions. Okay, so where we'll begin is we'll have a definition of what exponential functions are like and then start looking at their properties. Before we go further, though, I wanted to contrast exponential growth and linear growth. When we've worked on linear growth before, if you have a linear function, the original value from the range increases by the same amount over equal amounts found in the domain. And what that means is if you have a function like f of x equals 2x plus 3, the slope is constantly 2, is basically what this means. Is if you wanted to take the difference between f of 5 and f of 7, okay, let's go ahead and calculate those two. It's good practice. So f of 5, 2 times 5 is 10, plus 3 is 13. F of 7, 2 times 7 is 14, plus 3 is 17. Okay, those have a difference of 4. Okay, between 13 and 17. If you take f of any other two numbers, f of 102, and we'll make those 2 units apart, so f of 104. Okay, I just picked those out. But what's important is that they're 2 units apart. Okay, f of 102, 2 times 102 is 204, plus 3 is 207. F of 104, 2 times 104 is 208. 208 plus 3 is 211. Okay, the difference between 207 and 211, 4 units. Okay, so the increase basically is constant, right? And that's why the graphs end up straight. A exponential function, by contrast, the increase is not by a fixed amount, it's by a percentage increase. Okay, another way to look at the difference is this. Let's say that you have 2 job offers, okay? You just got a job after graduation, or 2 job offers after graduation, and job A is going to offer you $40,000 a year, and then you're going to get a $2,000 a year raise. Okay. Job B is going to offer you $40,000 a year also, but they're going to offer you a 5% raise, 5% annually raise. Okay, assuming that the 2 jobs are otherwise the same, which job should you take? That is, how do the salaries compare? So let's think about how your salaries will be changing over time. For job A, you'll make $40,000 in the first year. Then you'll get a $2,000 raise and make $42,000 in the second year. And then another year will go by and you'll be making $44,000. One too many fours. $44,000 in that third year. One more year goes by, you'll be making $46,000. Okay, so we could figure it out. I'll leave it to you to figure out, okay, after you've been there 20 years, you know, how much are you going to be making? Okay, job B, you make $40,000 in the first year. Okay, and then you're going to get a 5% annual raise. So 5% is going to be $2,000. So you're making $42,000. And then the thing is that here, in going to from the second to the third year, we're not just going to add in another 2,000, because your raise is 5%, and we need 5% of 42,000, and that's 2,100. Okay, so you'll be making 44,100. Okay, then another year will go by. And you'll get a raise of 2,205. And be making 46,305. Okay, so you can tell that after the 4 years, the 2 salaries are not the same. In the first case, the amount of increase that you're getting each year is a flat 2,000. In the second case, the increase each year is a percentage of the current amount. And so that's why the amount that we're adding each time is changing, is increasing. And that increasing by a percentage is a characteristic feature of exponential functions. Okay, so we have another example to illustrate. Okay, so let's say that we have a little town, and it's got a population of 800. The population, we know, grows by 4% every year. We want to find the town's population after 5 years. Okay, so let's go ahead and figure this out. So after 0 years, that's when we were just starting, the population is just 800. Okay, in the first year, or after 1 year, the population is going to go up by 4%. So we'll have the 800 initial population, and then we'll add to it 4% of, so multiply 4% of that initial population. Okay, and so 800, 4% of 800 is 32, right? So this will go up to 832. In year 2, we'll take that initial population, not initial population, but the year 1 population of 832, and add to it not 4% of 800, but 4% of 832. Okay, and that'll be 33.28. So it'll be 865.28. Of course, here, it doesn't make sense to have fractional individuals, so we could round when we get to the end. But the point here is that we're going to increase by that 4% at each stage. Another thing worth pointing out is the calculation that we're doing here in row 1 here for 800 plus 0.04 times 800. We can write that if we factor out the 800 as 800 times 1 plus 0.04, which is 800 times 1.04. And then in a similar way, the 832 times 0.04 plus 832, we could factor out that 832, and we'll have 832 times 1.04. So rather than multiplying and adding, we can just do one multiplication by 1.04. Let's try that one more time. For row 3, it was 865.28. Let me just round that down to 865. 865 plus 0.04, 865. The 865 factors out, leaving 1 plus 0.04. And that's 1.04 times 865. Let me put the 865 in the front. Okay, and knowing that is going to help us, because if we wanted to know, what would be the population after 20 years, you don't want to be here all day multiplying and adding. And so we're going to want to be able to come up with a formula for it. Okay, continuing onward, I went ahead and filled this out for us. Continuing onward, it ends up with the population in year 5 is 973. So studying the calculations and how they're shaping up, we saw that we took the prior year's amount, multiplied by 0.04, and then added. Okay, so in row 3, for example, we had 865 plus 4% of 865. If we factored out the 832, that's, some of those are off. Those need to be changed. Too much copy and paste. Factoring that out, we can see that advancing from year to year, we're going to multiply by 1.04. All right, so I fixed some of those values. Sorry about that. So in each case, we take the prior year, multiply by 0.04, and then add it to that prior year. So that, in effect, is multiplying by 1.04. In order to get further into the future, we would continue multiplying by 1.04. So repeated multiplication would be raising a number to a power, and so we'd end up with this function, n of t. So here this is standing for n of t, number of things. That's our population. T is our time, which is going to be in years. 800 is the initial amount, and then 1.04, representing our growth rate of 4% annually. And that's raised to the t year. So we can use that to help us figure out future values if we want. So we can make t be after 25 years, or 20 years and 25 years. So for 20 years, that will be n of 20, which is 800 times 1.04 raised to the 20th power. We'll get a value here in a minute. And then for 25, it's similar, only of course we'll be using 25 instead of 20 for the time. Okay, so then we can figure those values out. So 1753 about. And then 2133 after that. All right. So this has been an example of an exponential function. The kind of definition from our book looks like this. We're defining an exponential function for any real number x. So the domain will be all real numbers. An exponential function is a function of this form. F of x equals a b to the x. By the way, if you look in different books, you may see different formats. Other books I've seen define this as f of x is a to the x, and they leave off that constant multiplier at the front. We're going to try to stick with the version that our book has. but in spirit they're the same. The A is a non-zero number called the initial value. B is any positive real number that's not 1. The domain is all real numbers. The range is positive numbers if A is positive, and negative if real numbers if A is negative. And then the intercept, the y-intercept is 0A, and there's a horizontal asymptote at y equals 0. Okay, I did want to mention just a tiny bit about the initial value. So if you have a exponential function that looks like a b to the x, and you evaluate f of 0, remember the time is going to be our variable here. So at time 0, we'll have a times b raised to the 0 power. B raised to the 0 power is 1, and so we'll just have a. So the value of the function at time 0 is going to be a, which is why a is called the initial value. All right, so what we're going to do next is work on the graphs of these functions just a little bit. The next section, 4.2, deals more with the graphs, but we just want to get a little bit of a taste here. So we'll do two of the most simple exponential functions, the 2 to the x function and the 1/2 to the x function. So let's take 2 to the x first. So I'm going to figure out the values of 2 to the x for these select x values, and that I've just chosen these because they're relatively easy to compute with. So let's do that. So 2 to the 0 power is 1, 2 to the first power is 2, 2 squared is 4. Okay, easy enough. We're multiplying by 2. 2 cubed is 8. Okay, 2 to the minus 1 power is a half. 2 to the negative 2 power is 1/4. And 2 to the negative 3 power is 1/8. Okay, so let me go ahead and draw these. So we'll have the point 0, 1, 1, 2, 2, 4, and 3, 8. Okay, on the negative x side, for negative 1, we'll have 1/2. For negative 2, we'll have 1/4, and then by the time it's 1/8, you just kind of have to fake it. All right, so that is our basically our exponential function. So you'll notice that it is increasing. It is always greater than 0. The horizontal axis, it turns out, is a horizontal asymptote for the function. The domain is all real numbers, so we'll go ahead and write that out. The range is the open interval, 0 to infinity. The asymptote is the line y equals 0. And here, when I say important points, there's 2 points that this graph will always pass through. It's going to pass through the point 0, 1, and 1, 2, 1 for this one. No, 1, 2. All right. So why is that? And this is true for any function, exponential function. The part about the important points. So let me address that. If f of x is a b to the x power, then f of 0 will be a b to the 0, which is a times 1, or a. So when x is 0, y is a. So the point 0a is on the graph. For this particular example up here, sorry, there's a piece missing, and I'll have to fix that. For this particular example, the 2 important points on the graph are the point 0, 1, and 1a, but the a is the value, the 2 value, the base here. Okay, the reason that I've divided this into 2 separate graphs, one for 2 to the x and one for 1/2 to the x, is that the behavior of the graphs depends on the base. If the base is bigger than 1, we're going to end up with this kind of strictly increasing graph. Moving on to the 1/2 x, this one, we'll see that the graphs are all kind of the same basic shape if the a is in between 0 and 1. Okay, for the base. Okay, so then again, we're going to calculate 1/2 raised to the x power for some values. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. For 1/2 squared, that's 1/4. 1/2 cubed is 1/8. 1/2 to the -1 is 2. Then we'll have 4, then 8. So once again, we're going to draw those dots onto our graph. So we'll have 0, 1, 1, 1/2, then 1/4 and 1/8. So that should be looking kind of like the mirror image of the left half of our previous graph. For -1, we'll have 2. For -2, we'll have 4. For -3, we'll have 8. Okay, so this should look like our last graph, but reflected across the y-axis. And in fact, it is. It is going to have the same domain as our previous function, and the same range, and the same asymptote. Okay, and it'll also have the same important points. It's going to pass through point 0, 1, and 1, 1/2. Okay, so that's it for this first part of the video. We're going to go on to looking at some applications, specifically first with compound interest. We'll do that in the next video. Let me know in the meantime if you have any questions, and have a great day.